Hi everyone, in this session we're going to go a little abstract. We're going to look at the von Neumann, the Harvard, and the modified Harvard architectures. And we'll go through each of these three in order. So von Neumann first, then we'll look at the Harvard, and then we'll look at the modified Harvard architectures. First off, the von Neumann. So it's been around for quite a long time. It was introduced by a fellow, John von Neumann, in 1945, so before I was born. And it consists of a control unit, the ALU, or arithmetic logic unit, a register set, and then also a region for memory. And then, of course, the ability to interact with input-output devices. So the memory region contains program instructions and also the data. And it has a single memory area for program instructions and for the data. So it's only one memory location. And here's a visual representation of the von Neumann architecture. So this particular architecture is easy for circuit designers. All the code and data is in a single memory region, we can see down here. So we have one memory region. Simple, but there are some issues, as we'll see. The main issue is with this single memory space, so this area down here. So you can see here are three components of the processor, right? The control unit, the registers, and our arithmetic logic unit, or ALU. So the issue here with the memory is there's two things. There's the fact that it can be a performance bottleneck, and also that there are issues with security. And we'll take a look at each of these two issues momentarily. Excuse me. First off, the bottleneck. So the single memory space requires multiple memory cycles for instruction and for data access. So that can be an issue. Most programs work with data stored in memory allocated separately from program instructions. Now, we can use cache memory, and this has become a big part of modern processor design, is this idea of cache. And we're going to talk quite a bit about this a little bit further on in the course. So the shared communication path to the processor is still the main issue. So all of the data and all of the instructions vying for the same path to the processor. So that's a bottleneck issue. The other is security. So because the information is shared for program and data, basically malicious coders can store code as data, right? And that can be an issue because then that data can actually be run as code and do malicious things. So we can use this data and ask the processor to execute it, it being self-modifying code, and can do malicious things. For example, manipulate or delete other pieces of data. And the buffer overflow is a common flaw, and this can be exploited and was exploited in early processor design. So a hacker overflows the buffer, then rewrites the program's return address. So because the buffer was overflown, we rewrite where the program comes back to, and it comes back to an area of malicious code, for example, and that code is then executed. So it points to the malicious code rather than the original program. And so now basically the hacker can run any code that they want, for example, access information or data that they shouldn't otherwise have access to. So that can be an issue. Moving on to the Harvard architecture, originally implemented around the same time, 1 year earlier in 1944 as the Harvard Mark I. And it had one address space and a memory bus for program instructions, and a separate address space and memory bus for data, so separating program instructions from data. So the benefit of this is simultaneous access to instructions and also to data. But the one issue is that it doubles the instructions needed for the processor. Here's the Harvard architecture here, and you can see the difference, of course. At the center, we still have our CPU with our three components, our control unit, our registers, and our arithmetic logic unit. We still have our input-output devices. Of course, this varies depending on the type of system that's actually constructed. And then here we have our instruction memory. This is the main difference, our instruction memory and our data memory, so they're separate. So that's the kind of the main difference between the von Neumann architecture and the Harvard architecture. The modified Harvard architecture, several variants of this. They're used in modern computer design, so a little bit of both. collectively called the modified Harvard architecture. And generally, there's some degree of separation between programs and data. So we want to optimize as best we can with some separation, but typically some means of storing data also in program memory so that the processor doesn't have to do quite as much as it would with a standard Harvard architecture. And less commonly, the reverse. So also some means of storing the other way. So storing program memory and data, storing programs in data memory. So a little bit of vice versa, but less commonly the other way. Here's what the modern Harvard architecture looks like. So the former, not the latter, where we have our instruction memory, and we also have a little bit of data memory in there with that instruction memory. Again, just to optimize processor usage. Other than that, it's pretty much the same as the Harvard architecture. And this is what's used in many real-world computer systems today. Now, digital signal processors, or DSPs, achieve benefits from this type of architecture. So they can execute one multiple accumulate, or one MAC it's called, operation per processor clock cycle. And typically instruction memory is read-only, so requires constant data values only. And that's really all I wanted to talk about today. We're going to go a lot more into cache memory and the different levels of cache memory a little bit forward on in this course. And just to summarize then, we talked about three things. We talked about the von Neumann architecture, which has one memory space. Then we talked about the Harvard architecture, which has two memory spaces, one for data and one for instructions. And then the modified Harvard architecture, which allows a little bit of data to be stored in the instruction memory just to more optimize processor usage. And most modern architectures use the modified Harvard architecture. All right, so thanks for tuning in, and we'll see you again in the next session. Take care.